And now I would like to invite our second keynote speaker, Professor Shawqi Al Dallal, to give his talk titled Gravitational Waves from Colliding Neutron Stars, a New Era in Multi-Messengers Astronomy. Professor Shawqi, please take the floor.
I'm talking about one of the most important discoveries in the 21st century. Now, the story, when it started about 1 century ago, exactly in 1916. In fact, if we go to see the history of science, of modern science, we have 3 stops. The first stop is in 1900, where for the first time a theory what called the quantum mechanics was postulated. The second stop is in 1905, where we have the emergence of special relativity. The third stop is in 1916, where we have the laydown of what we call general relativity. Now, these 3 theories shape everything we know about science today. And I will pick up the prediction of Einstein's general theory of relativity in 1916 that there is something called gravitational waves. Now, we have in this century, we have 2 major discoveries. The first one is called the discovery of the Higgs boson, and this story started exactly in the early 60s of the last century. And it takes scientists 50 years to discover the Higgs boson. And to discover the Higgs boson, they build up the biggest machine you can imagine. It has a length of about 27 kilometers. And the data gathered to discover the Higgs boson is what can I say? Something that you cannot imagine. If you put the CDs, or for the data for the discovery, if you put it in CDs, and you put these CDs one upon each other, you will reach a height of 27 kilometers. So you can imagine how much data are required to discover this Higgs boson. Now, the second discovery, which is unbelievable, is the discovery of gravitational waves. Nobody was able even to think that these gravitational waves could be detected, for the reasons I will explain to you just in a few seconds. Now, if we go to the sky, we'll discover there are 3 types of objects, or dying objects. Stars, they are born in nebula, but also they die after a certain time, depending upon their initial mass. If their initial mass is too big, they die as a black hole. If their mass is a little bit smaller, they die as neutron star. And if their mass is even smaller, they die as white dwarfs. So in fact, there are 3 kinds of dying stars in the universe: white dwarfs, neutron stars, black holes. I will talk basically about the black holes and neutron stars. Neutron stars, I will show you in a minute what it consists of. So in fact, all stars, they are born, and then if they are too big, they end up as a black hole. If they are smaller, they end up as neutron stars, or if they are even smaller, they end up as white dwarf. Our sun will die and becomes a white dwarf. Now, in 1916, Einstein introduced what we call general theory of relativity. It is a simple equation in green. I have shown this equation. In fact, this simple equation If you want to expand it, it will take pages and pages and pages of very tough mathematics. It is a tensorial equation. Now, in this tensorial equation, scientists made many discoveries, in fact. So, what is the prediction of general relativity? First prediction is that the universe started sometime 13.8 billion years ago. Also, the theory predicts that the universe is expanding, and this is verified. A gravitational redshift of light, that means when light is emitted by an object, it has certain color, and as it goes further, the color changes. This is the explanation. I cannot explain it less than this. Massive bodies curve space-time around them. Also, gravitational lensing, how planets orbit the sun, and the most important, which is our subject today, is the existence of gravitational waves. So, in fact, we have to discover the gravitational waves, and scientists since 1916 tried really to discover these waves. And the most important step was in the 60s in UK by one of the scientists, but it was not successful. To discover these gravitational waves, we have to really go for big machines. And I will show you what kind of machines we need to discover these gravitational waves. I'm trying, in fact, to make things simple. I'm trying to avoid the technical part. The technical part of my talk today is accepted for oral presentation in COSPAR conference in Pasadena, USA, the coming summer. So, in fact, how we know that gravitational waves exist? There's a certain prediction by general relativity. So what scientists looked at, they spotted two neutron stars. They are about 1 million kilometers apart. And they discovered that these neutron stars are approaching each other. The period, they are turning around each other in 7.75 hours. And this time is shrinking at a certain rate. Now, they can check how this period is shrinking against the theory of general relativity, and discovered, yes, general relativity predicted that the rate of shrinking exactly as observed. So, in fact, these two scientists, they've been given the Nobel Prize in 1993. Their observation was in 1974, and they waited for about, you can see, about 30 years or so to get the appreciation of their discovery. Now, if we look at space, everybody thinks that space is just an empty thing. No. Space is like a plastic. And this is a result of general relativity. What I mean as a plastic, that means if you put a mass, a huge mass, in space, then this mass will curve the space around it. So, for example, in this case, I am putting big object here, and the space around it is deformed. In fact, this idea was confirmed in 1919, just 3 years after the emergence of the general theory of relativity. Now, gravitational waves. The first gravitational wave started or emitted at the beginning of the universe, 13.8 billion years ago. And scientists try hard to discover this ancient or old gravitational wave, but they've been unsuccessful. At certain time, a few years ago, they thought they discovered it, but it turns out no. I will not talk about this. I will go further. Now, how to discover a gravitational wave? The best way to use interferometer. In this interferometer, I have a laser beam. Now, the laser beam from the left comes to a splitter and is split into two sections. One section up and one section to the right. And they join each other, and there is a detector. Now, if we go inside this beam, we will see this is the beam. So in fact, there is interference of the laser beam inside these tubes. These tubes is around 1 kilometer long each. And if there is a gravitational wave hitting these beams, what will happen? One of the beams will be longer than the other. By how much? Here's the catch. By 10 to the minus 15 meter. It is the width of a proton. Something you cannot imagine. And the technology is how to detect a change in length or interference pattern caused by this small change in the size of the beam. So in fact, this is a schematic diagram of black holes, and I have a laser beam running in these tunnels, each one about 1 kilometer long, and then the beams are form interference pattern, and the interference pattern could be destroyed by the passage of a gravitational wave. Once it is destroyed, it is detected to the left. Sorry, to the right here. Okay. Now this is the one of the detector. In fact, scientists built 3 detectors. These detectors cost billions, and it takes about 30 years to build them. The first 2 detectors are called LIGO. And LIGO, we have 2 LIGOs, one in Livingstone and the other, I think, in Hanford. These two detectors, they are far apart. It is very important to build at least 2 detectors. Why? Because to be sure what is happening here is happening 6,000 kilometers away. So if there is a gravitational wave hitting the Earth, it should hit every part of the Earth. So hitting 2 things which are far away. These are the 2 detectors, LIGO detectors, one at Livingstone and the other at Hanford, thousands of kilometers away. And there's a 3rd detector. This is called Virgo. Virgo is an European detector which is built in Italy. So we have 3 detectors, in fact, to detect gravitational waves. And these 3 detectors are capable, if they are synchronized, to identify in what direction in space the gravitational wave is coming from. Now, observation of the first gravitational wave from binary black hole merger. This happened on 14th September 2015. In fact, if there is a discovery of a gravitational wave in detectors, scientists have to be sure that it is so. And to analyze the data, it takes at least 3 months. So, in fact, if it happens in 14th of September, it will not be announced until December or the year after, in January the year after. Now, the first one The frequency was 35 to 250 hertz. The masses of the black holes, the emerging black holes, the first one is 36 sun, and the other is 29 sun, the mass of the sun. You can imagine how heavy these black holes are. Of course, there are black holes much, much more massive than this. There are black holes who are millions or billions of suns at the center of galaxies. Now, if you add 36 plus 29, you get how much? 65. Whereas the final black hole has a mass of 62. The difference of 3 solar masses being spent to produce energy of gravitational waves. So the gravitational waves produced by the collision of these 2 black holes, in fact, is equivalent to 3 solar masses. Now, where this happens, it happens at a distance of 1.34 billion light year away. I don't know if you can imagine how far it is. To give you an idea, the nearest star is at about 4 light year. The galaxy is 100,000 light year. Okay, we are still not a million. The nearest galaxy is 2.4 million light year, and this is 1.34 billion light year away. Even though we've been able to detect such a collision from such a far distance. Now, I will see if I have some simulations, but it seems that okay, these are the data from the first collision of black holes, and these red, blue, etc. These are coming as registered by different detectors at Hanford and at Livingstone. At that time, Virgo was not operating, so we have only 2 detectors working, and you have gravitational waves with frequency increasing. When they merge, of course, everything goes to 0. So they start with certain, to the left, with certain frequency. The frequency increases, and when they collide, everything goes back to 0. Now, the question is, how many events been discovered using these detectors? The answer is about 6 events. The last one was this one. We have 2 black holes. One has a mass of 7 suns, and the other has a mass of 12 suns, producing 18 solar mass black holes, and 1 solar mass is radiated as a gravitational wave. Now, this makes a history. 17th August 2017 will be remembered for a long time, because this is the first time we discover the merger of 2 neutron stars. Why it is important to discover the merger of 2 neutron stars? The answer is simple. There is something called gamma ray burst. Gamma ray burst is one of the most fascinating phenomena in the universe. You can imagine the sun turns to radiation in 1 second, in gamma rays in 1 second. Just like this, evaporated in 1 second. It gives an energy of about 10 to the 51 joule. So 10 to the 51 joule is produced in 1 second, just evaporated. This is called gamma ray burst. The energy of gamma ray is very high energy. Now, scientists have been looking, what is the origin of these gamma ray bursts? And they postulated two origins. The first is dying stars. A star which dies and collapses on itself and disappears as a black hole. The second is the collision of neutron stars. Now, the collision of neutron stars never been observed before, directly observed before. So on 17th of August 2017, there was detection of gravitational signal. Look, it is only on 16th of October that confirmation of binary neutron star merger. It takes about 3 months, 2 or 3 months, to be sure that there is a collision between neutron stars. Now, here's some data. A frequency increases from a few tens of hertz to 600 hertz. The masses of the neutron stars, 1.2 and 1.6 solar masses. The galaxy is NGC 4993. This is the name of the galaxy. We have billions of galaxies. Of course, we have to have some system of nomenclature for these galaxies. The distance of the event is, the galaxy, which is 4993. The distance to that galaxy is 130 million light years. That means light will take 130 million light years before, much before the dinosaurs. So what we are looking at, an event which took place much earlier than the dinosaurs. In fact, here, I'm just showing you a video. These are gravitational waves, and I have 2 neutron stars dancing before colliding. So let us see what happens. You have seen it. Space telescopes all over the world, they spotted, you see the arrow to the left. This is how it started. This is the galaxy, and this is the event where the colliding neutron stars took place, and to the right, it be shifted or dimmed, and you can see how the dimming of the light is generated. I will go further here. Now, look at this figure. This is very interesting. Now, you have here very interesting data. The first, you can look up to the left. The second row, you can see a violet spot there, a violet spot. This spot took place 1.74 seconds after the arrival of a gravitational wave. This spot represents what we call it gamma ray burst. So the gamma ray burst arrived 1.74 seconds later. So we received first the gravitational wave and then this one. And this was a headache for scientists for a long time, I think until now. They should arrive at the same time. So why because gravitational wave, they have the velocity of light, and gamma ray, they have also the velocity of light. So why the gravitational waves arriving 1.74 seconds earlier? Now, if we look at the second, you have the X-ray. X-ray generated after the collision was spotted by these satellites. Swift, you have many satellites, Nexstar, Chandra, Integral, etc. The ultraviolet was seen only by Swift and Hubble Space Telescope. If we go to the optical, look at the number of satellites register the phenomena. You have over 30 satellites registering this phenomena in the optical region of the spectrum. In the infrared, also we have tens of satellites registering the phenomena. In the radio, we have many space and Earth-based stations who discover the phenomena. So in fact, this phenomena was discovered by, I can say, tens of satellites and Earth-based stations. Now, one simple question: where you and me come from? Doctor? No, we are coming from all this combination. Because at the beginning of the universe, we have only hydrogen and little helium generated. Okay? Later on, stars were formed, and the stars explode. When they explode, in fact, what is a star? Is a factory. Is a factory turning helium or hydrogen into helium, helium into carbon, carbon into oxygen, etc. And when they explode, you have all these elements in space. So in fact, all elements consisting me, you, this building are coming from stars. Now, of course, we can see what type of astronomical event produce each of these elements. For example, I have some coming from the merging neutron stars. You know, all this violet colors are the dark violet colors are coming from merging neutron stars. And other elements as well. So in fact, all elements are coming from stars, not necessarily emerging neutron stars, but from stars. Yeah, they said I have 2 minutes. I will try to. Okay, I think you are interested here. Gold, how much gold? In fact, scientists, they calculated how much gold is generated by colliding neutron stars. And there are many ideas. Some of them, they estimated some few moon masses of gold. Some of them, they estimated some few earth masses worth of gold. And a simple calculation, if we have 16 neutron stars binaries in our galaxy, and you have one neutron star merger every 50,000 years, then we can have 100,000 of earth masses of gold are generated in the universe. So you can see how much gold is generated in the universe. The gold you have in your necklace is not born on Earth. It was born by very violent events in the sky. Conclusion, the discovery of gravitational waves opens the horizon of a new field of astrophysics that enables scientists to probe deeply the nature of our universe. Thank you.